So today we'll see how a transistor is used as a switching device. Basically, I'll use a BC547 NPN transistor to switch an LED, right? But first, let's just make a basic connection and see how LED would work, right? Although this is basic, but let's see. So first of all, this is a breadboard that I think everyone probably would know. These are the power rails. These are the pins where our components would go. Basically, one parallel segment is connected to each other, so they are all at same potential level, right? And similarly, in the power rails, these all are connected to the same voltage level internally, right? Okay, so basic LED connection would be something like my battery would go here, right? This and then this is the LED that I'm using. In this the long pin is the positive terminal and the negative is the negative, and the short one is the negative. So right, and I negative terminal I'm connecting it to the ground, right? My black one is the ground, this one is the positive part of the battery, positive terminal of the battery. My battery is a 3-volt battery, right? And again connecting the circuit, right? And the LED works. So in terms of the circuit, this is how the circuit looks like. This is my positive, this is my battery, right? 3-volt, then goes the resistor 1k, and then is my battery LED, right? And then this is connected. So this is the positive terminal, then this terminal I'm connecting to the one side of the 1k ohm resistor, this connection, then this goes to the LED, right? And then I connect it back to the ground, right? And now measuring the voltages. Okay, so the voltage around this is somewhat around 1 volt, right? 1 volt, and voltage up across LED is 1.8 volt. So our LED consumes around 2 volts, right? And rest of the voltage is dropped across the resistor. So going back to our circuit diagram, this was 1.8 volts. So applying KVL, so 3 volts would be equal to, right, let's say this is V plus 1.8. So V is 3 minus 1.8. It's about 1.2 volts, right? And that's what we were seeing. Now, according to Ohm's law, I into R is 1.2, so the current in the circuit is 1.2 by 1K, around 1.2 milliamperes. Okay, so this is the calculation. Now, also confirming this in our circuit, bring it back. So, yeah, since ammeter is to be connected in series, let's see. Yeah, this one. I connect the ammeter into series. So yeah, if you see, it's around 1.2 milliamperes. Okay, so this was coming about 1.2 milliamperes. The circuit was 1.2 milliamperes, and we know that our LED consumes around 1.8 volts. Right now, let's say in this circuit, if we wanted to control the switching on and switching off of this LED via some sort of switch, right? So one way was to connect a manual switch where we would just our switch would basically just break the circuit and connect the circuit back to kind of achieve what we want, but that requires manual intervention, right? What if we wanted to do this electronically, right? So for that we need some sort of a switch. That's where our transistor comes into play, right? This is a BC547 NPN transistors. So what it does is it has three terminals, right? So collector, base and emitter, and basically we send the voltages at the base terminal control the current flow at the collector terminal, right? So we can control the current flow at the collector side by giving some sort of current or voltage at the base side, right? I think I would rather keep it a little practical than go into the theoretics of it, because I really don't like doing that. But okay, so now our next aim is to control the switching on and switching off of this light using this transistor, right? So what basically we would want to do is we would connect this, so our LED would be working as our load, and that's we would connect it to our collector side, and then we will control its operation by controlling the current in the base terminal, right? So first of all, let's go and study the circuit diagram. So this is what the circuit diagram would look like. This is our load, right? Load, and we knew that this consumes about 1.8 volt, so for current calculations, right? And this is our base terminal. So whenever basically how this is a common emitter configuration, and whenever we give some sort of volt, we'll kind of keep it simple and give it 3 volts only, right, directly. And whenever we give this signal to it, basically the base emitter junction will get forward biased, right, and it would act as a forward biased diode, and voltage drop of 0.7 volts will be seen across it, right? And this basically would make this circuit act as a short this transistor act as a short circuit, and our effective circuit would become something like this. right? So our circuit would be complete and we would see LED on, right? And when we remove this voltage, our circuit, this base emitter junction would behave as a reverse bias, and thus a transistor will act as open circuit, as an open circuit, and our equivalent circuit would be something like this. So this would be off, right? Okay. And also, since this is a diode, we don't want to directly connect a high voltage to the base terminal, because that would damage our transistor, as so high voltage would cause overheating, and it might burn our transistor. So that's why any excess of the voltage, we want that it should drop across a resistor, right? And only a safe amount of voltage, enough to forward bias a diode, uh, comes across the base emitter terminal, right? So this is a circuit. Now I'll make the circuit in the circuit diagram in the breadboard. So this here I've connected. So now at this point, I've connected the collector terminal to the negative side of the LED, right? So basically this connection is done, and emitter needs to be connected to ground. That's why connect the emitter to the negative terminal. Basically it's our logical ground of the circuit, right? Because every other uh, voltage measurement will be happening through this. Now okay, this is done. This is my 560 ohm resistor. I could have chosen any resistor. This is just because I had this one lying around, right? And this would be my base resistor in the base side, and okay, so now my circuit is complete. I'll connect the power supply, right? And this is my input, right? Now the circuit is complete. Now if I apply the positive voltage to it, it does not work. Oh, let's see what has gone wrong. Yeah, I think some connections were loose. So okay, when I apply the voltage to the base terminal, it switches on the LED. Okay, now let's measure the currents on all currents and voltages, right? So let's see the connection, the voltage across the base emitter junction, right? It should ideally be, since it's forward bias, we would expect it to be around 700 millivolts or 0.7 volts. Okay. So yeah, if you see, it's around 0.7 volts. Yes. So since this was 3 volts, according to kVH, this would be the voltage across this resistor would be 3 minus 0.7, that is 0.3 2.3 volts, right? This is coming about 2.3 volts, so this matches. Now we knew the earlier from our earlier experiments that the so yeah, so now we knew that from the earlier experiments that the voltage drop across this LED is around 2 volts. So that is 2 volts, then same as earlier. And since this is 3 volts, so this current in the circuit still remains about 1.2 amperes, right? So this way our transistor is basically acting as a switch, as this signal, right, this voltage is right now it's coming from our battery, but in a circuit this voltage could come from any kind of sensor or some other circuit, right, which wants to switch on this light, and this LED could have been some other circuit or some other sensor or speaker, right? So that's how transistor acts as a switch basically, right? So current in the base region is controlling the current in the collector region. Okay, now I haven't talked about the DC current gain and other parameters of this transistor, how that is working, probably because I didn't want to do that right now. But in this circuit, what we are basically doing is that we are making the transistor work in two modes, that is cutoff mode and the saturation mode, right? In saturation mode, what we are doing is we are forward biasing the base collector region and the base emitter region. Base emitter region we have forward bias by providing a voltage, positive voltage at the base end, right? Since this is a P terminal and emitter is the N terminal, so that basically forward biases the base emitter region, and any other additional voltage drops across this resistor, right? Similarly, what we are doing is now the base is at a positive side, positive voltage, right? At this end, the collector pin is at a slightly lower voltage, so that's why the base collector region also acts as is operating at a forward bias region, and that's how the transistor, sorry, is moving into the saturation region. So no matter what the current in this base terminal is, our current in the collector terminal is basically saturated at a point, and it would not increase by the DC current gain of this circuit. It would have gotten to a maximum value, right, and limited by the resistances, of course, right? And that's how this circuit works. And when we switch off this base region, basically we're cutting off the input supply. That's why our our transistor goes into the cutoff state, right? Okay, thank you.